This lecture is about energy conversion. Now, sometimes people talk about energy production, but we can only convert energy from one type to another. For example, mechanical energy to electricity, heat to mechanical energy, or light energy to heat energy. And we'll see how that is going in this lecture. Now, first of all, we have to look at the places where that happens, and these are the power stations. There are, as you see, a lot of different types of power station, and thus we divide them in two basic types. The one basic type of power station, and that is the most often used power station, is a so-called thermal power station. What you do there is you generate heat by some source, and then you convert that heat by a thermodynamical process into electricity. Now the main fuel is in most cases fossil fuel. Fossil fuel like coal, gas or others. And so what you produce is steam, and this steam is directly driving a turbine, and this turbine is connected to a generator. Then we have gas turbines, we have combined steam gas turbines, and we have diesel generators. That is in some cases a cheap way to have small power stations, sometimes for backup. The next fuel is nuclear. Nuclear is usually producing heat by a process with uranium, or maybe in the future with thorium or fusion. But what you produce in all these cases is steam, and this steam can then directly drive your turbine. A new way to produce this heat, no, it's not that new because it was really invented 100 years ago, that should be mentioned, in Egypt, is concentrated solar power. So you have two possibilities. You can build a huge tower and collect the sun, or you have a mirror system at the ground, and both of them are built to produce hot steam for the conversion. And there is one interesting technology that never really lifted off. It is geothermal. In some areas of the world you have volcanoes, and you can use the hot rock to produce steam. Or even in low temperature areas like in southern Germany, you have some places where the rock is so hot in some 5 kilometer deep that you can produce steam for energy production. So this is a part of thermal stations, and there are non-thermal stations where we use a different force to drive the generator. The best known is hydropower. Hydropower was also the first type of energy that produced electricity, and of course it was the first type for other mechanical use like a mill, and even today we call factories a mill because they were driven by hydropower. You have different small deviations. So a runoff river, for example, at the Rhine Valley you find dams, and the water is collected and running a turbine. You have sometimes reservoirs, as in the Swiss Alps, or also in Germany, or in Black Forest. Schluchsee is a little bit a type of reservoir. You have pumped hydro, where you actually don't produce power itself because you use overproduction power, and then you can drive a turbine with this water that you pumped up before. And another thing is tidal forces at the coast. There are some places in the world you have high tides up to 17 meters, then it makes sense to build that, but it is not economic at the moment. The big new player in renewable energy is wind. You can put your wind onshore or you can put it offshore. Depending on the wind speed, you have different efficiencies and economic viable places. And the largest potential for energy is photovoltaic, because we have so much sun on the earth that we could easily run all our economic with photovoltaic, but it is a little bit expensive and difficult because at night and in wintertime we don't have the light. It is a very tricky process that you convert the light into electricity that is based on quantum mechanics. And by the way, Einstein did some work in this area. Usually it's silicon based or some other materials that can convert photons. Now look into the path that we usually have. So these are all the energies again I talked about: nuclear, fossil fuels, bioenergy, geothermal, direct sun, wind, hydro, and ocean energy. And then we try to collect that energy and finally to bring that to energy services. The first thing is some of them are fuel based. So you can take the fuel and bring it to the conversion station. So you are independent of the place. And at the place where you want to produce the electricity, in most cases, you put the thermal conversion there, generate heat, and this heat is now used for two things. The one thing, you can use the heat directly for rooms, or you can use it for kinetic conversion. That means typically you run the turbine and have electricity, and then you have all the electrical energy services. This path is the widest used, and actually fossil fuel, solid fuels like coal, that is the main path today where we run our energy system. But it's not the only one. Geothermal, for example, you cannot transport the geothermal because the earth has to be hot at that place. For example, in Iceland, then you install the geothermal conversion factory of a power station at the place where you have the hot steam, and then you can use it, yes, whatever you want to do with the heat. Heat something. In Iceland, for example, they heat even the streets to that it is not slippery in the winter time. That's a very interesting way, because heat is cheap from geothermal, or you do the conversion way. If you run sun, then you can use the sun to produce gaseous fuel. For example, if you have some corn, you can produce gaseous fuels, but that is not so efficient way. The standard way is that you directly put the light into the lighting and heating service. So you can put it on your rooftop and you can heat your house, or you have a window. A window is in some way a lighting service. So you open that, and the window is a fence terra, is the place where light comes into your room. Or you use it a little bit more indirect. You start with the energy, produce electricity, and then you can do everything like this. Wind, hydro, and ocean are mechanical forces, and these mechanical forces can directly be converted in an electric generator. The difficulty is you need huge towers and huge blades that you can catch a lot of wind. You need hydro dams to catch the water. And the situation at the ocean is even more complicated because the ocean is a tough environment. The water is full with salt, and that is not really the best thing for your metal turbine. So this kinetic energy can now be converted into electricity, of course, but you can also put that directly in work. And in historical times, we have seen windmills, and we have seen water mills, and we have seen sailing ships. Sailing ships are nothing else than using wind energy for kinetic energy, and the work is done, yes, by driving the ship and using some mechanical services. For example, cutting, if you have a mill for cutting wood or whatever. So this is the basic way path to convert energy. Now, all these conversions are not equal. Some of them are widely used, some of them are not so widely used, and all of them have some losses in there. And if we look into that, we see the basic sources again. We have the crude oil, and the crude oil is going most of the time into transportation. A small part is going into feedstock. You want to generate something for the animal, or you have to work in agriculture. And some parts are going directly into the industry. Remember that we can produce products like steel or aluminum. Steel needs, for example, heating by crude oil sometimes. And we can use the oil at home to heat our houses. Then we have the coal. Coal is also going into industry and nether into transportation. Now, in the early days, there was this small way, that is the steam powered train, but they died out. And I think only in North Korea there are still some, or in some museum places. Most of the coal does that way. It is converted into electricity. That's a big path, but there is a significant path going into industry for steel production. Natural gas is going a lot of different ways. It is going a little bit into feedstock. It's going into transportation. In the rare cases, you have gas cars driven by natural gas. And the big thing with natural gas is that you use it directly at home to heat your rooms. And some part is going into conversion steam in gas turbines. Hydropower, of course, never makes it into the transportation, or that's actually not completely true. In the early days, they had some hydropower driven trolleys, but that is really gone. And you convert hydropower directly into electricity. That's the main path. Nuclear power is also going directly into electricity. There have been plans to put that into airplanes and so on, but that is not true today. And biomass is widely used for heating your house. That means you have furnace in your home, and then you can heat your house. All the paths have numbers on it, but we have gone already through that. You see the big sources have a wide bar here. Crude oil is the main driver, and new renewables are small in the moment, but they have the highest growth rate. And so you have always to be careful what year this information is coming from. This is about 2010 or 12, I think. It has grown a little bit, but not too much if you look overall the energy sources. Now comes the standard production of electricity by coal. And what we have here is, in some way, a disaster. You buy the coal, 100% of energy is in the coal in a chemically bounded way, and then you actually use that for power generation. But this red line shows that we lose a lot of energy during the power generation. So that is lost. I should really tell that. That is lost energy. So only 35% is making it into electricity, but during the transmission process, a small amount, 1.5%, is lost in its wires, and something is less lost in the transformators and the wiring at home. Now that doesn't count too much. But then if you go with your energy into a light bulb, then in an old-fashioned light bulb, you lose again more or less just everything. Then you have the light shade, and then you use light if you're not in the room, and finally only 1% of the whole energy is arriving where it should. This is, I think, one of the worst case scenarios how to waste energy. 100% and only 1% is used. Of course, we can make it at every place a little bit better, but there are limitations and we have to understand them. There's entropy, and you can watch a video about entropy here. It's a German video. I really like it. Try this video. Now, the global market for power and different sources is changing, and in the moment what we see is a huge growth in photovoltaics, the yellow bars here. And we are not actually talking about the volume of energy that we produce. We talk in this slide about the power plant market. So power plant market is something for the big boys. Big companies build power plants. In Germany, it's Siemens or Westinghouse or General Electric and some others. And in the traditional world, they usually build nuclear power stations, coal power, oil power, gas power, and hydropower. That was the world. It's sometimes growing, sometimes going down. What happened here? There was this East Europe revolution, so they teared down a lot of power stations. Then the economy was growing again, and so new power plants came in. And sadly enough, the coal power plants were widely installed. Other types of power plants have really gone. For example, oil. 40 years ago, oil was a significant part. Today, just no one builds an oil power plant because oil is too expensive. It is more useful to use it in car or airplane. The hydropower dams are still under development. A lot of them are built every year. Some 10 megawatt, some 10 gigawatt or 10,000 megawatts, and new types are coming in. That is very renewable. We see wind power started a little bit earlier. Wind power is not so difficult, and so wind power rose. And today, if you look into the market, 2014, but it's still growing, half of the investments is going into the deployment of wind and solar. And if you add hydropower or another renewable source, you see that most of the deployment is renewable. The renewable sources, And this big bar of coal is in China, because China is really expanding its coal power station capacity. All the other types of energy converters are small. Biomass, yeah, let's say biomass is also a little bit renewable. So no one today builds new gas power stations, but be aware, sometimes the numbers are small, then they are big, then they're small again, then they're big again. So there's a big dynamic in this market. So the market is not constant, and this is hard for companies to keep working in the market. Same is true for nuclear power. There has been a boom in the 80s, and then you see this bar get very, very small. Today we don't build new nuclear powers at the moment. The global power generation capacity, this is now more or less the integration of the numbers you have seen in the slide before, is what is the capacity? The capacity is if you add up all installed power stations, and because you add them up, you get real big numbers. And so we are talking about terawatt hours a year production capacity. So coal is leading. Lignite coal, one of the worst things we know, that is producing a lot of carbon and is widely used in Germany and Poland. By the way, Germany is the largest user of lignite coal. There are historical reasons. I don't want to go in the detail of that. Gas is there, and sometimes we had a lot of installations. Diesel is minor, very small. In some special cases on islands you use them. Nuclear is more or less constant over the last decade. And here, this is the new renewable energy. So we usually talk about new and old renewables. Why do we do this? Because they came in the last year, or in the last few years. Hydropower is also renewable, but it is an old renewable type. It is not old. With hydropower plant can be very new, but it is from the old type. Especially solar and wind are the big players here. But you see, it is still very small. What's that? That's a nice picture I took some years ago. It is in Iceland. You see this volcanic rocks in the background, and what happens here is they convert the hot steam coming out from the ground into electricity by these converters, and there is an awful lot of steam in the air because it's quite cool and wet air in Iceland, and so you'll see that. By the way, the used water is then flowing into a small pond or lake, and people can bath in that lake. Maybe that are people taking a bath in this hot water. It's maybe 30 degrees Celsius in here, and it's fun to be there. And the steam that is coming out from the underground is, of course, much hotter. Otherwise, the conversion would not work. So this type is geothermal. Geothermal energy. Not at every place available, but in some spaces it is. The top areas is, of course, Iceland, but also in Italy, you know, they have volcanoes. There is some business in California, in New Zealand, and other places in the world where you have a lot of volcanoes. But this is a nuclear power station. Nuclear needs in the conventional way we use it today, a big vessel here. By the way, this is not necessary for the reactor itself, it is for security. In the case that the reactor gets demolished, you have a lot of hot water, and that water would evaporate, and to keep that hot water and all the other stuff in there, the radioactive material, you build always a big concrete containment. And this big concrete containment is one of the major costs. It's a 1.5 meter thick wall and a lot of steel in there to keep the steam in, just in case that there's something going wrong. And we had these cases in Fukushima, and sadly we didn't have this containment system in Chernobyl. So in Chernobyl the reactor ran away and there was no containment, so all the stuff was going into the air. And the other buildings around here are typically used for the conversion. That means steam is going through turbines and very conventional technology. But it's huge. You see the cranes doing all that work. I think it is happening in Finland here. Now, after the solar energy, this picture I took in Mongolia. This is Professor Ennewisch. He is enforcing solar power in Mongolia. How is this usually constructed? Very simple. You have some steel piles driven directly into the ground. That is easy in Mongolia. They have a good ground for that. And then you put hundreds and thousands of these modules on the steel supporters, and every of this module produces about 300 watt when it is sunny. That is the peak energy power peak, the highest power this can produce. This site here, yeah, it is some hectares. This is a site with 10 megawatt by the way. It's south of Ulaanbaatar, and they want to expand that in a really large shape up in the gigawatt range. Let's see what's going on there. So that is one place with a large, huge PV. So if you look on a global scale into that, there is a map showing you the different types of energy in the world. And so South America is driven by hydropower. That's interesting because they have cheap hydropower, they have rivers, not too much density of population, and so they can live on hydropower. The same is true for Africa, more or less. Then we have a part of the earth where we use natural gas, that is Middle East, East Europe, and of course some parts here in Europe. Then, and that is not really fair that they painted for solar at the last part. So where happens solar? Solar happens in California, in South Europe, and a little bit in Germany. And other sources like wind. Wind happens in the East Atlantic. That is because the wind is blowing here for meteorological reasons, and so Spain and Portugal, Ireland, Scotland, and here northern Germany and Denmark are the places where you have a lot of wind energy. And all the other places, yes, okay, here natural gas, it should be mentioned, United States is also a lot of gas. Natural gas is happening here. And so you see, it is mixed more or less. India has a lot of coal and so on. Coal, yeah, we should mention that. Coal is really heavy used in this China, North Asia area, and also in India. That is the big coal eaters. Now look into the coal plants. This is a map of all the coal plants in the world, and you see news are popping out that are the red ones and that are the old coal plants. Just no new coal plants are built in the old industrialized world of Europe and United States, but in Asia and in India we see new coal power plants popping up. If you're interested in this topic, I recommend you to go into that website. They have interesting and amazing stuff about coal power. And of course, this is described by a coal lobby. They see all the advantages of coal, but be always aware if you go in these websites that they are a little bit unbalanced in their ideas. Yep, so coal has a disadvantage. The air is smelling, the air is not clean. This is a picture from Peking where we have dust in the air. And so you see here just no skyline. Reason it is so dirty air. It's hard to breathe, and I really get a choke had to choke all day because the air is really disaster there. Now, primary energies that are the sources for this conversion process, and so we have the hard coal, and this is again the last 10 years how the world has changed. You see hard coal is growing and natural gas is growing. Other sources are more or less stable. There is a glimpse of solar and there is the biomass, but biomass is a traditional biomass more or less that is constant over time. It is more or less wood burned in the third world. Ocean energy geothermal doesn't play any role, and it's hard to see hydro. Why are they now so small? Because we are talking about primary energy. You have always to know that if you look, for example, into hard coal, only 1/3 of it is really going into electricity, and the others is lost. So, and that's always true. You lose a lot of the energy and only a small part is really going into the services you need. Natural gas, okay, your service might be thermal heat, so you have a higher efficiency in as long as you only talk about the services, but there's also some parts lost. In solar, you don't have the loss, but the part of solar is still very small. Now we will see the Carnot cycle. It should be mentioned that it is a quite tricky thing, and it was an understanding of the physics behind the thermal machine after the invention. So the steam power was invented in the 18th century, and more than 100 years later, the theoretical basement for this technology arrived, and it was Professor Carnot who did the fundamentals. And I don't want to go completely through this physics because it's a little bit tricky, but let's look what they want to present us. And there are two things in this Carnot machine. The one thing is that you have a cycle. A cycle means you start at one point in volume and with a special pressure. So this is, for example, maybe here the starting point. You have a pressure. The pressure is symbolized here by these weights, and the volume is in here. It is within a piston. And then you change something. In this case, you change the pressure, going from 1 to 2. The pressure is going down to a lower level. And from this point, you keep it, and now you change the temperature. You keep the pressure and you change the temperature, and then you have a lower temperature. So from 300 degrees Celsius to 200 degrees, whatever. And then you go back and reduce the volume again. So the pressure will rise if you reduce the volume, and then you rise the pressure, and then you end up with a higher temperature. So that is more or less the cycle. And the interesting thing is now that the space within this strange shaped thing, it's a type of a double hyperbolic plot here. This inside here is the energy that you can squeeze out, the mechanical energy you can squeeze out of a system. So if you want to have a wider area here in this bright shaped thing, you can do different things. One thing is, and that seems to be the easiest thing, you start out with 300 degrees Celsius, so you start with a higher temperature. And then you add this additional area. And so if you have this additional area, now let's paint this additional area also here. No, I only painted a little bit here. So then you squeeze out more energy out of the same process. And you can also go to higher pressures or lower temperatures here. That's also possible. You can add some space here. And all of this adds the efficiency. Now, but what you never can do is you cannot completely fill this area. You would need infinite temperatures and infinite pressures, and that is out of our technology. So now, if we go now to numbers and the relevant things, is that it is relevant for all thermal machines. But it should be mentioned that every thermal machine, like a steam power, a gas turbine, and so on, has a little bit a different diagram. It may look a little bit square shaped or whatever. Even your fridge has this diagram because your fridge is nothing else than a so-called Carnot machine. It works in a different direction. It goes not this way around, it goes the other way around, and then you cool down the inside of your fridge, or if you have an air conditioner, the inside of your room, where we always are in this strange shape area. So it defines our maximum efficiency. It should be mentioned that the real world efficiency is not exactly this. The real world, you have wheels and you have barrels and you have a lot of other mechanical processes that reduce the efficiency, but the core efficiency is defined by this. And now if you want to understand how is the efficiency, you need only two things. And the one thing is you need the temperature of the cold side. So the cold side is this lower temperature here. And you need the temperature of the hot side. So in this case, it was the 300. These are the two things you need. And if you have this, the low and the high temperature, then you can calculate the efficiency, eta. It is a 1. 1 would be the perfect efficiency. And to have that, you should not subtract too much. So if you want to subtract a very small number, you start with a very low temperature. Then you divide that temperature by a very high temperature, and then you subtract a small amount here, and then you have high efficiency. So try to make this small. If that is small, then you have high efficiency. Now, when is this number small? The one way is reduce the lower temperature. The lower temperature is more or less defined by our environment. We have typically 20 degrees Celsius around here. So we can't use, for example, minus 100 degrees Celsius. Actually, don't call it with a Celsius scale. You have to use the Kelvin scale. So the absolute temperature, the Kelvin scale, is the Celsius scale is Kelvin scale plus a big number, 273. So if you really want to do these calculations, be aware that you don't use simple Celsius degree. Otherwise, you could go to minus, and that would work very nice. So you have to use this Kelvin scale. And if you can't go colder than, for example, say, yeah, you use typically cooling water, maybe it's 20 degrees. So 20 Kelvin, no, not 20 Kelvin, 293 Kelvin, because that is 20 degrees Celsius. And the highest temperature, so look out for what your vessel can keep. So you usually take steel, and steel works up to 600 degrees, maybe. So here 890 Kelvin. So that's always Kelvin. And so if you divide that, now you are quite good. And so you should have a theoretical efficiency in the range of 60%. Yeah, reality is not that nice, but the theoretical way is there, and there are systems in the range of 60%. We will see in the next slide. So this slide is showing us a typical thermal power station. A typical thermal power station is heated by coal. So, and where does this happen? Now inside here, that is the burning flames, and there are today very tricky ways that you take the coal, you mill the coal, then you blow the coal into this chamber, and then the hot air is coming out, and then you start to catch this temperature, a high temperature cycle, a medium cycle, and a low part, so that it is really optimally transported to this place, and this place is a turbine. And you see there are two turbines, the first turbine and the second turbine. That's the low temperature area, high temperature, low temperature. And you connect the axis with an electric generator. So this is a generator here, and this produces, of course, the electricity for your grid. So we start with the high temperature process. We try to be as hot as possible, but be aware you have to use some metals here, and steel is more or less the best way to do that, but steel has limitations in temperature. And these turbines can be optimized. There's a lot of high tech inside using this for computer models and so on, but they are also at the limit. And here the cooling, the cold side. Yes, what you usually do is you have a cooling tower and you spray some water in here that cools down the water inside here of this pipe, and here are the clouds coming out, and that is more or less the lost energy of your process. Now look into this steam turbine. Here you see a steam turbine, and you always find this shape small to big. Then you know somewhere here the pressurized steam is entering the system and is expanding all the way out here. And here is it really hot. That's the hot place, and up there is the cold place. And because the steam is expanding over this path, the wheels and shovels get wider and wider. So steam turbines have a high efficiency because they are spinning, and you have not too much loss in the aerodynamics. It is a simple mechanical construction. That is a big thing, because this wheel spins with thousands of rotations per minute, and that has to work for centuries. Not for centuries, for decades, so 10, 20, 40 years. And all that should be stable over this long time. And that's a big advantage. You don't need ceilings and stuff like that. The geometric shape is quite complex, and there are only a few players in the world that really do that. That's Siemens and General Electric, for example, who build this sophisticated shovels in detail. and with a long life and warranty. So hopefully these two workers have not too often to open this for maintenance. Now, look here, that is a list of all the companies who do that. That is steam turbines, and a little bit similar are gas turbines. We'll learn that next slide. And here you see, as already told, Siemens and General Electric are the big players in the steam business. And some other companies like Alstom and a lot more here are the big players in the gas turbine market. Right? No, sorry, I mixed that. This is sorry, let me go back. This is, it was wrong. So the steam turbines are the red one, and the gas turbines are the blue one. So the General Electric and Siemens are gas turbine big players, but they also play a big role in steam turbine. Now, if you look into the details of the market, the gas turbine market is here led by General Electric, an American company, and we have this statistics. If that all happens exactly in the way as it's proposed, we don't know, but it is dominated by these two players, Siemens and General Electric. I think new Chinese players are coming into the business, and here you see Kawasaki also from other countries like Japan. Now there's one of the golden solutions for that. That is the so-called combined cycle system. The combined cycle system is the terminal system with the highest efficiency, and this 60% are not a theoretical value. That is a value we really can reach. And high efficiency reduces, for example, our carbon emission, and so everyone is trying to build like that. One disadvantage, of course, it is a little bit more expensive. Now look how that works. So it is combined. That means you have a fuel, and the fuel here is gas. It is not always methane. It can be a different gas, and you can even use oil, because if it is hot, you also have a gas. And this gas turbine here that is burning the gas is quite similar to the thing you see at your airplane. Your airplane is nothing else than a gas turbine, but not with using this energy for an AC power. It is for driving your airplane. Airplane turbines are very sophisticated because it is necessary to reduce the fuel demand in airplanes, and so this part is really working well. But at the end of the pipe of your gas turbine, there's what comes out of the gas turbine, hot air, and this hot air is going into a heat exchanger and heats steam, water, and then generates steam by that. And so you can add another system here, that's the steam turbine, and so you again generate energy. So maybe that you produce about 40% here in your gas turbine and 20% here of efficiency, and together they end up with 60%. So if we look into this plot, for example, we can see that coal power, because it's a single process, you can't burn the coal in a gas turbine. It has a high carbon impact, and so if you use different types of turbines, if you have a natural gas standard, you are on that track, and you combine it with another additional fuel saver, you have this lowest energy and this lowest carbon output per input per produced energy. So this is the so-called annual cross load. So if you load that, so you see the higher the load, the higher the demand, of a higher emission, but there's one disadvantage. Most of its gas turbines work only a few hours or a few thousand hours a year. Most of the coal is running just all around the year, by the way. Yeah. So now comes the last type of energy converter of this thermal type, and that's the diesel generator. What is a diesel generator? It is more or less a big diesel engine as you have in your car, and some people own a plug-in hybrid or a hybrid car. A hybrid car is nothing else than a diesel, or maybe it's a gasoline car, and you combine that with a genetic system or an synchronous machine that is generating electricity. So out there comes the electricity, and it's all on one axis. So here you usually don't, in the large systems, you don't use a car motor, you use motors from ships. Ships have big diesel engines. They are optimized for long haul and very low operating cost and so on, and you combine them simply with a synchronous machine. The efficiency is not so high, but it is very flexible. You can use it at any place because you can put that in a container. You see that is prepared for container shipping. You put it at your site, for example, in an island, and then, or in emergency as an emergency power supply for your computing department. If you have a large computing department like Google or so, you need something like that, and then you can start it whenever you need. Within 1 or 2 minutes, this is on speed. It's not perfect efficient, but it is easy to produce energy any place, electric energy at any place.